The submarine sends signals. For example, I have a ship. This ship moves in the water to see a specific target. This target reflects the signals back to you, and then it starts receiving. It will tell you how much time it took for the signals to reach your point and return. For example, it took a certain time. Okay, 1 second win. 1 second win. Good, this time is good. I have, how much is it in the water, for example? Which is, for example, good. I can determine my target or not. Yes, of course, you have the distance over time. In this case, if you want to know the speed, it's speed in time. The time you calculated here is considered as going and coming back, or the total time. So, if you take the distance, it will be the total distance, which is going and coming back. Not one way, meaning two ways. Going to the target and coming back. Therefore, you need to divide this value by 2 to give you the distance. This is the same idea, folks. The same idea in my probe when I send my pulse. I want to know where this pulse came from when it was reflected and returned to the probe. I want to know where it came from any location. So it starts saying, I will send this specific pulse with this specific frequency at this specific time. Then it starts calculating, saying, well, now I know my field and view, my field of vision, or the cross-section I see of my sonar image. I want to determine the X and Y coordinates of where this signal is coming from. So it starts telling you that this signal returned in this amount of time. Okay, since I know the speed, I will consider relying on it, or this is what I am working on in my calculations. Then it starts to tell you that in this case, you should start to get what is available on it, the one that I got from my calculations, or I can get the depth that is available on it, the one that I got from our calculations. So in general, the efficiency increases the velocity, but overall, the efficiency has significant concepts regarding the propagation from the density window. As a result, the pulse that comes out has a specific shape. The pulse has a wavelength and a specific frequency, and it has a certain amplitude. We said that I have the frequency and 1 over t, which is the period of one cycle. The period of one cycle, which is t for me, is represented by this shape. The pulse itself has something called pulse duration, meaning that this pulse does not consist of just one cycle. Rather, it is a collection of cycles, which could be 2 or 3, depending on the frequency I am working with. For example, if you want to work with high frequency, the number of cycles that will occur in a certain time will be many. In this case, the outgoing pulse will take this shape. The total time from the beginning of the pulse to the end of the pulse is the pulse duration. The period is the time for one cycle. If you want to know the pulse length, how long the pulse is, what you do is get the wavelength of one cycle and multiply it by the number of cycles. For example, I have this pulse, and it turns out to be how many cycles? 1, 2, 3, for example. So that's 3 cycles. I get the wavelength from here to here and from here to here. I'm sorry, that's 1, 2. Consider this 3, for example. Okay, I have one cycle. Here's the second cycle, and this is the first cycle, and this is the third cycle. I got the wavelength, then multiply it by the number of cycles to get the pulse length, which tells you how long the pulse is, where it starts, and where it ends. That's the pulse length. The pulse duration is the total time of the complete pulse. Here, it expresses, of course, as an example, that the relationship between frequency and wavelength is an inverse one. An increase in frequency will lead to a decrease in your wavelength. If you consider the velocity to be 1540 meters per second, by calculation, at 10 megahertz, you will get 0.1 to 0.15 millimeters. At 6 megahertz, 0.26 millimeters. At 3 megahertz, 0.5 to 1 millimeter. And at 6 megahertz, 1 millimeter. Now we have talked about pulse duration and pulse length. I mentioned that I currently have two types, high frequency and low frequency. We know that what determines high frequency is the thickness of my crystal, and low frequency follows the same story regarding thickness. We will talk shortly about what exactly you want to do next regarding the pulse. How do I generate this at high frequency, and how do I generate it at low frequency? Low frequency means that the number of cycles per second is low, while high frequency means that the number of cycles formed will be high per second. So high frequency means that the pulse length in high frequency is shorter than the pulse length in low frequency. The pulse length in high frequency is shorter than the pulse length in low frequency. Right. The pulse duration at high frequency is of a shorter duration compared to that at low frequency. The time and length of these pulses at high frequencies are significantly less than those observed at lower frequencies. Now, regarding our probe setup specifically, there is something called damping material or damping block, which I was talking about earlier. It's located behind what we refer to as either crystal or element in technical terms. Do you remember, perhaps as you may recall, the tuning fork? We said that when I gave an impulse, a pulse, to this tuning fork, instrumentally speaking, it vibrated accordingly. Then subsequently, something known technically as ringing occurs, which resembles somewhat like a tone sound effectually speaking. If one brings such an object close enough towards their ear vicinity, you will hear distinctly sounds akin, perhaps even similar, unto bell-like tones, or specific rings thereof respectively. This ring lasts longer durations, or ceases depending upon whether one holds on to said tuning fork properly aligned correctly, so forthwise. After striking aforementioned device making your own sound, if stopped its vibration process, what then happens next? Will auditory perception still continue hearing residual sounds emanating from it, or shall they cease entirely altogether henceforth? It will stop completely. So you have indeed applied damping to the vibrations of your crystal. The damping block located behind the crystal serves to dampen or stop the vibrations that occur due to the alignment of the crystal. There are two types of damping, light damping and heavy damping. Heavy damping is like stopping completely, meaning the pulse for you didn't take its time, it just barely produced the pulse for you. So you applied heavy damping, which means it stopped immediately. Consequently, the pulse length for you here will be short, giving you what is called short wavelength, which means high frequency. However, if you apply light damping to the existing crystal, the wave or pulse is still active, so this results in light damping, which gives you long wavelength and thus low frequency. Low frequency, indeed very low frequency. Okay. In the high frequency pulse that came out, it has a short pulse length due to heavy damping. The low frequency occurred through light damping, which resulted in a long wavelength, long pulse length, and long pulse duration as well. Now, what expresses the concept of damping is what I call Q factor, which relates to the long wavelength, long pulse duration, and long pulse. So, what expresses this concept is what I call Q. What I mean is the transducer Q factor. Regarding the topic I was discussing, I mentioned that I have something called bandwidth, where I have the shape of the beam or the shape of the pulse that comes out in this way. Here, I have the central frequency, and here I have F1 and F2, and here an F2. The bandwidth, in the context of signal processing, refers to the frequency ranges contained within your pulse that can appear in your pulse. If you are using high Q, what does that mean? It means that your bandwidth will be low because of the inverse relationship between the two. On the other hand, if you are using low Q, your bandwidth will be large in this scenario. Heavy damping gives you low Q. What does heavy damping mean? It means your pulse lengths have become short. You have high frequency and your pulse duration is low. So, if low Q gives you heavy damping, or heavy damping is represented by low Q, the bandwidth for you is large. A large bandwidth means the shape of the frequency spectrum of the pulse will look like this. Here is the center frequency, and here are F1 and F2. Your bandwidth is large, meaning the pulse contains a wide range of frequencies. Now, light damping creates long ringing, which I was talking about, but it will give you high Q. What does high Q mean? It means your bandwidth will be small and it will look like this. The bandwidth here is small, and this is the view. Here is the center, which is the resonance frequency. I call it the resonance frequency. This large curve is curve B, and this curve is curve A. Which one is curve B? The large one at the top. This means your bandwidth is large, which means your Q is low. All right? This means that your Q is low, which indicates heavy damping. In the case of the curve where your bandwidth is low and your Q is high, there is light damping. So, that's the explanation. When you want to perform organ imaging or Doppler, you use a transducer that has high Q and narrow bandwidth. This means that my bandwidth is small, indicating that my Q is high, and the low bandwidth means that, in this case, you are using this transducer for organ imaging. So, the high Q means that your ringing time or downtime is large, which means that your frequency is low, not high. When the frequency is low, this helps the probe or the pulse that comes out not to get attenuated within the tissues, allowing it to reach a greater depth, which aids in organ imaging or imaging of different organs. In contrast, the Doppler transducer has a wide bandwidth, short pulse length, and high frequency. So it works on shallow or surface imaging for me, and I use it in Doppler. Therefore, if I am talking about Doppler, I am referring to a low Q transducer, and if I am talking about organ imaging, I use a high Q transducer. All right, doctors, in the days of Genghis, it was used on the high. So, the high Q, Dr. Islam, what does it mean? Let's connect everything together. High Q means light damping, right? What does light damping mean? It means you didn't stop your pulse all at once. You let your pulse rise, increasing the duration of the pulse. So, your pulse duration increased as if you stretched the pulse. Stretching the pulse means you increase the wavelength present. When you increase the wavelength, what happens to the frequency? The frequency decreases because there is an inverse relationship between wavelength and frequency. So, high Q resulted from light damping, which increased your wavelength and decreased the frequency. This also affected your bandwidth, which is represented by that curve. This is a high Q, which is a curve. Why is it created? It creates a narrow bandwidth. In this case, you are using a narrow bandwidth, but with a high frequency. The frequency you are working with is fine. The bandwidth is small, but the frequency you produced is low. I'm sorry. The frequency you produced is small. So, this small frequency is the probe that gives you whether you are using it in organ imaging or in Doppler. Low-frequency organ imaging is important because you want to reach a good depth. High-frequency, Dr. Islam, means that the ultrasound pulses will interact significantly with the tissues and cells inside the patient's body. This enhances the attenuation of the pulses. When we talk about interaction, I will clarify this point further. When the pulses come at high frequency, the interaction between these pulses and the cells increases, leading to a loss in intensity. Consequently, the intensity that reaches the dips you want to image will be very weak, resulting in a very weak signal being reflected back to you. Therefore, the signal that returns from a certain dip will be weak and you won't see anything. In contrast, when using the Doppler, you are more concerned with the surface area and do not need to reach high dips. You just need high resolution. So, using a high-frequency transducer gives you your resolution, as we will discuss later regarding image quality. The advantage of high frequency is that it allows you to deliver fast pulses. These fast pulses are done by Dr. Islam to reach a specific object inside the body. All right? There is an object behind it. You send a pulse, then another pulse behind it, and another pulse behind that, and so on. You are increasing the pulse rate frequency. So, what does this fast frequency do or help with? It helps. I might not explain it to you right now, but I will explain it to you, God willing. It helps you to be able to differentiate between what is inside at a level called something, and this makes things happen more clearly. With high frequency, right? This is the relationship between the quality factor, bandwidth, central frequency, and the damping that occurs. Here are the same curves I was talking about. This is the broad bandwidth, and this is the narrow bandwidth. The broad bandwidth means your quality factor is low, while the narrow bandwidth means your quality factor is high. A low quality factor indicates heavy damping, while a high quality factor indicates light. Damping. This is the damping block that stops the pulse or allows for light damping or increases your ranging. The special pulse length, whether short or long, is the length of the pulse itself. So far, there is no problem. 2. You see this panoramic view? As you can see, this is the bottom of the transducer. What is this view? This view represents the shape of the beam coming from the transducer. You can notice here, they take a cross-section here in this area, and in this area, and in this area, and you see this view. Where is the area that has more homogeneity, or a cross-section with high homogeneity in the beam? No. This cross-section is fine. Okay? This cross-section still has incomplete homogeneity. The homogeneity here is less. Why? Simply because I have my transducer, and I said it doesn't have just one crystal. It doesn't have a single element. It doesn't just have one crystal that produces the alpha sound pulses. No, I have a set of crystals present, and each crystal produces alpha sound pulses. These pulses create what is called constructive interference. And this constructive interference occurs in the first area, which is called the near field. This area is called convergence. Convergence occurs here, meaning there is still interference happening between the beams. Okay, come on, so you can visualize it with me. Let's assume that this point represents an element or crystal, and there is a point next to it, and there is another point next to that one. This is essentially the output of the first point, which fundamentally produces the pulse in this way. In essence, the second point, or basically the second element, will essentially produce the pulse in this way. The third point is exactly this. What happened is that there is undoubtedly interference at this point, which is, in fact, certainly the intersection points between the pulses. When these points are coming in this manner, specifically, and the signal comes with this shape, and the third signal comes with this shape, I call this constructive interference. In this case, your signal will be strong. In this case, your signal will be strong. And what if this signal is... There are different groups coming in, and one is coming this way, while the other is coming that way. This creates interference, and both signals cancel each other out. This phenomenon exists in the initial area of my field, until your field starts to create what is called this area. Look here, you are in this area. The interference that occurs between this point and that point and that point and that point begins to create a specific area in a certain region that I call the front. This front is the area where there is the highest constructive interference and the highest homogeneity concerning your pulses. This area is known as the focal zone. The focal zone is the area that comes after the near field. I refer to the first area as the near field and the area that comes after the focal zone as the far field. So the first area where convergence occurs, along with the interferences and constructive and destructive interference, is called the near field. After this interference occurs, the best homogeneity, or the best focal zone for me, is the area where the homogeneity is very high and the signal here is bright. This is the highest point, meaning that the divergence starts to increase, which means the beam begins to spread out. The pulses move away from each other and divergence begins to occur in the far field area. The initial area, which is the near field, I call the frinal zone, and the far field I call the frinoper zone. The length of the near field depends on what? And the divergence angle is the angle between this area. You can see this angle. It is between your beam and where it extends, between this line and if you move in a straight line. The angle between this line and the actual divergence is called the divergence angle. Here, this is the first area I call the near field, which is the frinal zone, and the second I call the frinoper zone, which is the area where divergence or separation of the beam occurs. The focal point is the highest area. I have, which contains the homogeneity in the near field area or in this area, taking part of the near field. After the focal zone, there is another part of the far field that I call the focal zone. This area is considered to have the most homogeneous beam present in this region or zone. When you perform imaging, your focus is adjusted to this point, meaning this is the area or region that provides the best image quality or resolution. This is if I am using one focal point. If there are transducers that are referred to as multifocal points, they can make the entire near field area have multifocus. As we will discuss later about focusing, This gives you the highest resolution in the near field. Now, here is your transducer